This meeting is being recorded.
In this video, we will begin with section 1.8, which is a review of valence bond theory, and then we'll talk a little bit about molecular orbital theory as well, because there's not too much that we have to review about valence bond theory. But if you recall, this is where we count valence electrons, and this specifically here is a graphical kind of representation of how electrons, valence electrons specifically, interact to form bonds. So they like to use, the hydrogen atom commonly. We'll see that on the next slide. But these two electrons here in this first image are separated a certain distance. They can, and each electron, these dots, right, this is like the particle form of electron, is also represented by a wave here, right? So these are two different representations of the same electron. We bring these waves closer together. The internuclear distance, the distance between the two nuclei of our atoms, gets closer. Then eventually, if certain conditions arise, we can find constructive interference and a bond would form. If we see down here this destructive interference that results. So these two electrons were oriented in a way that their waves had destructive interference that resulted in a node formed. We would not see a bond here, so no bond down here, only a bond with constructive interference. So again, say these are two hydrogen atoms, right? There's a certain distance that comes between them, and then we get this overlap, if you see, right, of the two orbitals, and this head-to-head overlap of these two s orbitals, right, say this was hydrogen, would form a sigma bond, a single bond between the two. And if we did a cross section, that's what's shown here, that single bond. So this would be a sigma bond. So those were valence electrons overlapping, and a brief review of sigma bond formation. So in this next slide here, we're going to be taking atomic orbital wave functions that overlap, and they form what are called molecular orbitals. So these molecular orbitals, this is a different theory that has the whole molecule in one orbital now. So the entire molecule, these molecular orbitals, we add up atomic orbitals. So say this was, a hydrogen atom, right? So H2 here, we have the one hydrogen atom over here, one over here. Each has an electron, and it's in the 1s orbital. So this is the atomic orbital plus another atomic orbital gives us, down here, we have our first a spot where we could place electrons, and this would be a bonding molecular orbital. And then up here, we would have an antibonding molecular orbital, which would indicate if a node were being created. So since there are only two electrons, we can stick them down here in this bonding molecular orbital. And this would kind of give us a hint that H2 would form. This would become a bond, and again, due to constructive interference, this would be a node formation and indicative of destructive interference. So again, we have these overlap of atomic orbitals, which these electrons go into bonding molecular orbitals rather than antibonding molecular orbitals to achieve the lowest energy state, right? So if this is our energy diagram here, this is the lower energy, right? So in this bonding molecular orbital. And they tell you why really don't need to know the specifics about this, but the antibonding molecular orbital is higher energy because it has this node. It creates a higher energy for that to form. And let's take a look here at some other images. So this is a molecule here. So we have CH3Br. So methyl bromide, right, is one way to name that molecule, or bromomethane. So we have our bromine atom up here, and then we have our carbon here, and then we have some hydrogens. So what we see are that there are two molecular orbitals that exist. There's more than two molecular orbitals that can exist for CH3Br, but we're going to focus on two here below. We see some orbital overlaps, but the main thing that we're looking at here is how these molecular orbitals are extending over the whole molecule, not the entire molecule, not just one atom. So each of these molecular orbitals can hold 2 electrons, right? So that's our maximum. And we saw that with the hydrogen atom, right? The bonding molecular orbital, we saw 2 electrons housed. And we have 2 specific molecular orbitals that we're going to pick out here. And the first is called the highest occupied molecular orbital, and that's how it's abbreviated, HOMO. And then we have the lowest unoccupied molecular orbital, and that's our LUMO. So these are the ones that are going to be forming the bonds, right, between the two atoms, right? So these are going to be in play, right, when we have these chemical reactions happening. So we'll talk more about HOMO and LUMO in a subsequent chapter, but I just wanted to introduce you and keep your eyes peeled for later discussion of these terms. And we will continue with 1.10 with the next video.